Hi, welcome to the Chicago Math Statistics problem sections. So today we're going to take a look at the sufficient statistics for the certain parameters. And let's start with this one. It's a pretty basic one. So let's take a look. So the problem we're working today is like let x1 and x2 to be two independent Poisson random variables with parameter lambda. So I defined, so let t and other statistics was defined as x1 plus 2x2. So then also we defined the conditional probabilities here. And so we want to show t is not sufficient for the lambdas here. Then the second one we said, if the t is not a sufficient statistic for lambda, then let's use the factorization theory and let's kind of find a sufficient statistic for the lambdas here. Okay. All right. So let's go ahead. And get started. Okay. Let's go to the whiteboard here. Okay. So we know the x1, x2, they are from the Poissons, right? With the parameters lambda. So we know the PDF for the Poisson will be x factorial lambda x and e to the negative lambda. Okay, so now let's take a look. So let's take a look at this conditional probability. It is x1 equal to 1 and x2 equal to 1 and t equal to 3. Of course, from the introductions, I know the t, we define the t as the x1 plus 2x2 here. Okay, so now let's apply the conditional probability. So this will be the probability, the t equal to 3, and the top will be the probability x1 equal to 1, x2 equal to 1, and t equal to 3. All right. Okay, so now for the t equal to 3, so first one is here. So we said x1 equal to 1, x2 equal to 1, t equal to 3. Since t is equal to x1 plus 2x2, so the top, basically, we are looking at the joint PDF of x1, x2 is 1, 1. That is the only situation to satisfy x1 equal to 1, x2 equal to 1, xt equal to 3. Okay, so the denominator is p, the tx t equal to 3. So we have two situations here. T can be equal to 3. The one will be x1 equal to 1, x2 equal to 1. Another one could be, so we have one situation, x1 equal to 1, x2 equal to 1. But also we can have another situation, which is x1 equal to 3, right? So x1 equal to 3, but x2 equal to 0 here, right? So this x2 equal to 0. Okay, so now let's put the joint PDF. Because x1 and x2 are the independent random variables, so the joint PDF will just be the multiply. So 1, 1 will just be 1 factorial lambda to the 1 e to the negative lambda, and times 1 factorial lambda 1 e to the negative lambda. Right, so the denominator, it will be the same thing here is 1, 1 lambda 1 e to the negative lambda times 1 factorial lambda 1 e to the negative lambda, then plus x1 equal to 3, so will be the 3 factorial lambda, the 3 e to the negative lambda, then times x2 equal to 0, so will be 0 factorial lambda to the what? Lambda to the 0 and the e to the negative lambda here. Okay, so now let's just try to combine a little bit. So let's take a look at this one's here. This term I can simplify. So this term I can simplify to the lambda square e to the negative 2 lambda. correct? So the same thing here, this is the same term. So this term can be simplified to the lambda 2 e to the negative 2 lambda. And this term here, it will be simplified to the 3 factorial is 6. And then I will have lambda. So this is e to the, so lambda 3. So I have lambda 3 and then e to the negative 2 lambda here. Okay, so now we can simplify because both all the terms, both numerator and the denominator have lambda square e to the negative 2 lambda. So I can try to factor these things out. So I will factor lambda 2 e to the negative 2 lambda here. So when I factor this one out, the first, those green part, it will be what? It will be 1 plus. Then what happened to here? I factor the blue ones here. I factor lambda square. So I will have lambda here and over what? Over 6. Correct? All right. So now this term and this term can cancel out. So I will have, so the answers here will be lambda 6 plus lambda over 6. Okay, so this is a final form here. This final form for this condition is it depends on the lambda, right? So I have lambda include. So I know based on the sufficient statistics, so T is not sufficient, right? So T is not a sufficient statistics for the lambda here. Okay, so now the second part here, this is the first part. The second part here, they said, now let's try to use the factorization theory to find the sufficient statistics, to find the sufficient statistic for the lambda. So let's see here, let's put the likelihood functions here, right? So the likelihood function will just be, you multiply the two PDF, so it's the, so here it will be x1 factorial, and then here this will be the lambda x1 e to the negative lambda times x2 factorial and times lambda to the x2 e to the negative lambda. Okay. So then we can combine a little bit. So this would be x1 factorial, x2 factorial. Then you have a lambda x1 plus x2 and e to the negative 2 lambda here. So by the factorization, so I will put this one, I will say lambda x1 plus x2 e the negative 2 lambda times 1 over x1 factorial, x2 factorial. So I can call this things is just a function of my x here. Put the kind of bold, that means x1 and x2 here. And then I can put these terms here. This is a function, right? So this is the function of the g with the lambda with some type of the, so I said the function x here. So now I know the x here, this is a function g here. So that is what? So now I know the x1 plus x2. Okay, so is a sufficient statistics for the lambda, right? So based on the sufficient statistic definition. So this is what we talk about is a factorization series here. All right, let's say it. So like I mentioned, this is a very simple, basic problem. So we can get familiar with what is the sufficient statistic mean. And that's it. And looking forward, to talk to you and our next topic here. Have a good day. Okay, bye-bye.